Should I start? Thank you. First, I want to ask you a question. What do you prefer, the blackboard or the whiteboard? You prefer white? Okay, then no need to erase. They prefer white. I prefer black, but I'm okay.
Why is it not visible to you?
No, but I'm comfortable enough with both.
Sitting very far, so
They are afraid of me, and they think I'm dangerous.
take the front. The seats are empty, you take the front seats.
Sir, that is surely not the reason.
No?
Take the front.
Okay. I'm not aggressive.
But your aura is so expanded that they
Yeah.
want to go away.
No, but if they prefer the whiteboard, for me it's no problem.
Come in the front row, these seats are empty. You come to the front row.
So it seems that you prefer the blackboard.
Yes.
Okay. I should have asked you, not all the audience. I was about to erase with my cell phone. Okay, thank you. Thank you. I will continue. No. Okay, so let us talk about the result I already announced, that if two convex functions have the same subdifferential everywhere, they are the same up to an additive constant. It's an integration result. Well, I will consider functions with an open domain. A common open domain. I mean, if they have to end up being equal up to an additive constant, they have to have the same domain. Okay, if they have different domains, one of them cannot be obtained from the other by adding a constant. So I assume that both have the same domain and that this common domain, let us call it C, is convex. There are refinements of the result with less assumptions, but the main idea is there. Then the result is if the subdifferentials are the same, then I will avoid the temptation of writing f minus g, because f minus g is well defined on C, but not outside C, because then I would be using plus infinity minus plus infinity, which is undefined. But, so I will say that there exists a constant k such that f of x equals of g of x plus k. Or if you prefer, I could say that the restrictions, the difference of the restrictions of f and g to c is constant. Okay? Well, this is a classical result in Rockefeller's book with a not easy proof. requiring many results. But in Rockefeller's book there is something else. There is an integration result saying how to obtain the function from the subdifferential. Okay, he gives an expression which is, I think it's called Rockefeller integration theorem, which gives you the function out of the subdifferential. So it's a formula, I cannot remember it now, it's related to cyclic monotonicity, but I'm not going to use cyclic monotonicity, but the expression is something like you fix x bar, and then here you have the supremum of some expressions in which the subdifferential of f at many points, not just at x bar, at many points appear. Okay? So you give me the subdifferential operator, not just at x bar, but everywhere, and then I compute f of x. From this formula, it also follows the result, because if the subdifferentials are the same, these terms are the same for f and for g. And then I get that f of x on the domain, f of x minus f of x bar is equal to g of x minus g of x bar, because these two terms are equal to this supremum, which is the same in both cases. And then this means that f of x minus g of x on the domain is equal to f of x bar minus g of x bar. So at every point, the difference takes the same value as at x bar. So the difference is constant. If you want, call it k, and then you have the k stated here. But this is only in C. Also outside C, because outside C, this is plus infinity plus k equal to plus infinity, which is true too. This is one proof. Complicated proof. Yesterday, when discussing with the Dasgosh, he said, maybe you can use a mean value theorem for directional derivatives because of the equivalence between subdifferentials and directional derivatives that we have just seen. The problem is that I am not aware of any mean value theorem involving one-sided directional derivatives. So I cannot use that. But there is a mean value theorem for convex functions. Thank you. So the theorem says, in such a situation, if you have x, y in C, then there exists Z in the segment xy. So this means the segment with endpoints xy, the convex hull of x and y. Such that, and there exists a subgradient at this point such that f of y minus f of x is equal to x star, z star, y minus x. This is a mean value theorem due to somebody called Wedgie, I don't know how to pronounce it, Wedgie? who published this result in the Journal of Mathematical Economics. In 1974. Then, using this theorem, the result is immediate, because F is convex. Yeah, this is for convex functions. But wait a second, because maybe it's not so immediate. Yeah, no, it's totally immediate. So, if we're assuming that the subdifferentials are the same, no, it's not so evident. One had to deal with the difference. So now I think that this work that I mentioned yesterday to Devdas doesn't work. The problem is that it would work if I could deal with the difference. But the difference is no longer convex. So I cannot use this mean value theorem. So no, this proof, now I don't see how to do it. Anyway, this proof, if it can be done, which is unclear, could not be in Rockefeller's book because it's older. It's from 1970. Okay. Also, I don't know how Wedge proved his theorem, but I have a more general mean value theorem which includes this one as a particular case for the class of so-called tangentially convex functions. But in my proof, which is not difficult, I needed the Hambanach theorem. Okay, so forget this proof. And now I will give you another proof, and I will tell you the story behind this proof. In 2008, in Kaohsiung, Taiwan, you know well. Professor Yin from Vietnam was teaching a course on convex analysis, and he left to the students as an exercise to prove this, which I think I would say it goes against human rights because it's too difficult, it cannot be an exercise. Okay? But a very brilliant, at the time, master student from the Czech Republic gave a very original proof, very elementary, which is the one I'm going to tell you. Then, in those times, I was the editor-in-chief of the journal Optimization. And actually, Nicholas Hatzisabbas told me, look at this boy, what he has done. And then I invited him to submit his paper to my journal. And then he did it, and the paper, we sent it to referees, and the paper was accepted. I can give you the reference here. Oh. So the author, Pavel Kocourek, and the title of his paper is An Elementary. I have access to optimization, so if anybody wants this paper, I can send him or her an electronic version. An elementary new proof of the determination of a convex function by its subdifferential. A very long title, but it's already too long to make it fully correct. I would say of the determination up to an additive constant, but this should make the title excessively long. And it's published in Optimization. Volume 59, issue 8, and 1231, 1233, just 3 pages, 2010. This boy, I'm not in touch with him since a little bit later. Then when he finished in Kaohsiung, he went to Barcelona to my place, but totally independently of me. So he didn't come to work with me, or he didn't come because I offered him any possibility. No, he came because there is the so-called Barcelona Graduate School of Economics, and they offer a master program, so he made a second master in economics in this consortium, the Barcelona Graduate School of Economics, which is a consortium of several universities, including mine. He spent, I think, 1 year in my university, and then he moved to NYU, New York University, where he made a PhD in economics. But I have no news from them since long ago. But very brilliant and very special from many points of view. Very nice boy and very brilliant, but not conventional at all. Let's put it this way. Okay? Well, what did he do? What did he do? He said, take any 2 points, x and g, in C. So I failed to prove it by that mean value theorem, but even if I succeeded, that mean value theorem is not elementary. As I said many times, the proof in Rockefeller's book is not elementary. But the proof I'm going to tell you is for school children, just using very elementary algebra. So he said, let's take 2 points in the common domain, and let's prove that the values of f minus g is constant. Okay, then he does the following. Consider the interval xy. Here is x, here is y. We have this segment. So subdivide this segment into m subintervals of the same length. So define xk equal to x plus k over m y minus x for k from 0 to m. By the way, this brilliantness of Pavel reminds me also a very famous anecdote which you may have already heard about George Danzig. When he was a PhD student, he was taking some course, And then one day he was late at the class. It was a Friday, he was late. When he went into the classroom, nobody was there, neither the teacher nor the students. But then he found the problems stated on the blackboard. So he spent the weekend solving the problems, and on Monday he went to his professor and said, I have done the homeworks, but I found them much more difficult than usual. And the professor said, these were not homeworks. I mentioned 2 open problems. So he had solved in a weekend 2 open problems, believing that it was a homework. So it's the same type as Pavel Kocourek. Well, then, so okay, this is x0. This is x1, this is x2, this is xm. Okay? We are on an open convex set, so at every point in this set, the subdifferential is non-empty. So at every xk, I can take a subgradient. In fact, as you will see, Pavel proved more than it's classically proved. Let's look at the proof and you will see what he proved. So X star is a subdifferential at xk, which is assumed to coincide with the subdifferential of G at xk. But in fact, he didn't need this equality. He just needed the intersection to be non-empty, which is of course weaker. If they are equal, the intersection is one of them, and then it is non-empty because we have subdifferentiability at every point in this open convex set, okay? So I take an element, so from now on the assumption is this weaker assumption. I take an element in the intersection. And then I write the subgradient inequality several times. Fxk plus 1 is greater than or equal to fxk plus x star k, xk plus 1 minus xk. Okay? This holds for k from 0 to m minus 1. And of course, this is f of xk plus 1 over m x star k y minus x. Okay? I mean, the length of this subinterval is the total length of the interval xy, of the segment xy, divided by m. Okay? Well, and I do similarly for G, but in the reverse order. Let me see, I don't want to get into troubles with subindices, so let me check that it is the best way of presenting the proof. No, the best way, I mean, it can be done, but the way I have written the proof is with xk and xk plus 1. No, it cannot be like this. No. So I think, well, I have no troubles with the sub-indices, but I think it will work like this. Okay? Or if you prefer plus, and here x minus y. And this is true for k for 1 from 1 to m. Do you agree? We are almost done. Now I will add all these inequalities. And I am left with what? I mean, imagine f of xk in the left-hand side, then this is a telescopic sum. Then I get f xk plus 1 for the last k, which is m minus 1. So I get f of xm. But what is xm? Y. F of sk for the first k. The first k is k equals 0. And x0 is x. But I am also adding here another telescopic sum. So I get the first or the last, which correspond to the last value of k, which is m. No, it cannot be. No, let's look at a different way. So the last, I knew that I would get into troubles with sub-indices. I don't want to have. No, okay, no, it's correct. So the first k is k equal 1. So I get here x0, which is x. And I also get this term for the last k, which is m. But xm is y. And now I have to add all these terms. And most of them cancel out. All of them except 2. I mean, because we have here opposite signs. Okay? But the range of k is different here and there. So 2 terms are left. The term which is here but not there, which is k equals 0, and this is x star 0, y minus x, and the term which is here but not there, which is the term corresponding to m. So x star m, x minus y. This is what I get. And now comes a very important observation. I mean, what I want to do, so I am adding inequalities. So what I have obtained is this inequality. Okay? Then, what I want to do is to let m go to infinity. The number of subintervals go to infinity. It seems that there is a little problem, but it's not true. The problem is that this also depends on m, but it doesn't. Because x star m is an element, is a common subgradient at xm for these two functions, but xm is y, regardless the value of m. So in fact, you can write something independent of m. Okay? So I am calling y star x star m because the dependence on m was misleading. There is no such dependence. And now that's it, because since this expression between parentheses doesn't depend on m, it's a constant. When I let m go to infinity, this goes to 0. So the conclusion is f of y minus f of x plus g of x minus g of y greater than or equal to 0. What is the same as saying f of y minus g of y greater than or equal to f of x minus g of x. So what's the conclusion? X and y were two arbitrary points. The value of the difference at y must be larger than the value of the difference at x. But we can interchange y and x. So they must be equal. So this function takes the same value at y and at x. So this function is constant on C. What I am doing is only on C. Okay? Do you agree that it's beautiful? Brilliant, I would say. Very elementary. What have I used here? Nothing, just the definition of subgradient. Now I'm sure you can remember this proof forever. I mean, I don't know how long ago I looked at this proof, and 2 days ago I was trying to recover the proof, and I didn't need to look at the paper by Koczurek. It's so clear. So it's fantastic. Some people are brilliant. Well, so we have already talked a lot, maybe too much, but there are still many more things to say about convex analysis, subdifferentials. There is much more to say. I didn't even mention my favorite topic in convex analysis, which is conjugate functions, Fenchel conjugate, which is a notion very closely related to subdifferentials. But we don't need, okay? So we will, when we go back, we are about to economics, then we will use subgradients or supergradients, but not Fenchel conjugates. So I don't need to talk about that. So was all this part on convexity, subdifferentials, etc., clear enough, or do you have questions? Well, anyway, tomorrow you can ask me if you find some doubt in what I presented. So it's time to go back to economics. Okay? Probably you already forgot that we are applying convexity to economics. What we have seen is that the definition of the cost function associated with a production function. So let me recall that we consider a production function which transform n inputs into one output. And the only assumption we have considered so far for convenience is upper semi-continuity. Okay? And for such function, we define the corresponding cost function, which is defined on R plus cross R plus N into R plus union plus infinity, which is defined by C of yp equal the minimum. We justify that the infimum is attained. The minimum of Px subject to f of x is greater than or equal to y. So the arguments of these functions are an output level and a price vector, and what it gives us is the smallest cost I can incur to obtain the desired output level y under the prices represented by vector p, if the technology is represented by this production function f. Now I'm going to make you a question. Forget the given production function. I tell you this function, but I don't tell you which was the production function that induced this one. Can you obtain f? I mean, can you solve this functional equation for f? I think it's impossible. But okay, you cannot recover f from C. But what can you say about f? Looking at this expression, you say, okay, for a given x, if I put here f of x, the inequality is satisfied, obviously. So f of x is one of those values of y which satisfy this inequality, and then if I replace E with f of x, because this is the minimum cost, it should be less than or equal to any cost compatible with this constraint. Yes. And this is true for every x and for every p. So this says that f of x, as I said, is one of the i's that satisfy this condition, one of the i's that satisfies this condition, so f of x is less than or equal to the largest or the supremum of those values of y, so that c of yp is less than or equal to px for every p. For every p. Okay? I mean, f of x is one of those y's which satisfy this inequality. I am saying this here. Then it's less than or equal to the supremum of all such values. I cannot say more. If you ask me to deduce f from f, I say, okay, I can construct this complicated function of the right, on the right, which is a function of x. Y is the argument in the maximization problem, and this is for every p. So p is not variable. The only variable is x. So the only thing I can tell you is that the production function you are hiding, which produced this cost function, is related to this cost function by this expression. I don't know what is f of x, but I can give you an upper bound for f of x. I cannot say more. Okay, is this clear? Okay, now let us state and prove an important theorem. Depending on? So what we are addressing is the problem is, given C, I can recover F. All the information you need in the right-hand side is C. If you know this function, its values everywhere, then theoretically you are able to solve this problem. Okay? And this is a function of x, which is greater than or equal to the production function that induced this cost function. Do you agree? Theoretically. It's not an easy problem. Okay, no. But you will see that it is useful. Okay? I agree. So now let us see a very, in this producer theory I am presenting to you. You should not complain about the difficulty of this expression. We all know that life is very hard. So, okay. Then, the theorem. Suppose we have a function I'm going to call it D, which, like cost functions, is defined like this. Is defined on R plus cross R plus plus N into R plus union plus infinity be such that the following conditions hold. For every p in R plus n, d as a function of y is non-decreasing and lower semi-continuous. D of 0p is 0. D of yp goes to plus infinity as y goes to plus infinity. And now fixing y, as a function of p, this is non-decreasing and superlinear. Are you familiar with these conditions? These are the conditions we saw that every coast function satisfies. I am just copying the list. And either d of yp is finite for every p, or d of yp is plus infinity for every p. So either it's always finite or always plus infinity. It could be a coast function. I mean, coast functions satisfy these conditions, but now I'm not dealing with a coast function. There is no production function. Somebody told me about a function, d, which satisfies all these properties. Then we are going to prove that it is a coast function. How? I'm going to define a production function whose associated coast function is d. Now, so the blackboard is too small. I don't want to erase this. Then, under all those assumptions, I define f be defined by this expression, but in fact with maximum instead of supremum. So I define f in this way. Then f is well defined quasi-concave non-decreasing which is a reasonable property for production functions. If you increase the amount of inputs, you produce more output, or at least the same. Well-defined, quasi-concave, non-decreasing, upper semi-continuous, which makes us happy because we decided that the only condition we'll impose on a production function would be upper semi-continuity. And the cost function. Associated with f is D. Okay? So this means that these properties that are satisfied by cost functions are actually characteristic of cost functions, because every function satisfying all these properties can be interpreted as a production function, because I can construct a production function which is quite nice, quasi-concave, etc., that produces D as its associated cost function. In particular, D could be the cost function. So maybe you had your production function, but you didn't tell me, and you only told me the cost function and said, find f. Then I said, I cannot, but the most I can say is that the production function you hide is less than or equal to this. So I will never be able to find your production function, but I will find another one which does the same job, which produces the same cost function as the one produced with your production function. Okay? So let's try to see this, to prove this theorem. Is the statement clear? Okay. So we have to prove everything in the statement. First, that f is well defined. What do I mean by well defined? Here, two things. That it takes values in R plus, and then the maximum is attained. Okay? So in principle, write it as a supremum, and then either it is attained, which will be the case, or it is plus infinity. But what happens if f of x is plus infinity? Suppose for a moment that f of x for some x is plus infinity. I mean, And then I cannot say if it's a production function, you cannot produce plus infinity. Okay? So what would this mean? This means, because it's easy to see that the set of y's that satisfy this condition is a half line. Well, it's a segment because we are in R plus. It's bounded below by 0. Why? Because D is non-decreasing. Please pay attention to the role that all these assumptions play in the proof. No one is superfluous. Okay? So, if one I satisfies this condition, then every smaller I satisfies it too, because D is non-decreasing in Y. Okay? So and of course, Y equals 0 satisfies this condition, because D of 0p is 0, and this is non-negative. So the sets of y's satisfying this condition is an interval, maybe unbounded, but also closed. Why closed? Because D is lower semi-continuous. Okay? Easy to prove. Then, if I prove that this is impossible, that f of x cannot be plus infinity, then it's clear that the supremum is attained. But what would this mean? This would mean that D of yp is less than or equal to px for every p. And for every y. Assuming this means that the set of y that satisfy this condition is the whole half line, R plus. Okay? But this is impossible because of this assumption. D of yp goes to plus infinity as y goes to infinity. So there cannot be an upper bound. Okay? So, I mean, the fact that it's non-negative, because in principle, if I define it with supremum, it could be plus infinity or even minus infinity. Minus infinity if the set of y's were empty. But it's not empty because 0 belongs, so forget minus infinity. Then the y's that satisfies this is something between 0 and an upper bound. Okay, and then the maximum is that upper bound which is non-negative. So now it is proved that f is well defined, so it goes to R plus without any infinity there, and that the maximum is attained. Let us now prove quasi-concavity. So I have to compute the upper level sets. So let's fix a level. I consider a non-negative level because for negative levels, the upper level set is the whole space. Because this function only takes non-negative values, okay? And then the whole space is convex. So what is the meaning of x belonging to this upper level set? This means f of x is greater than or equal to y. So f of x is the largest y that satisfies this condition. and I have here a smaller y. So this y satisfies this condition. Okay, because we saw that the set of y satisfying this condition is a closed interval. So this means d of yp is less than or equal to p of x, p times x, for every p strictly positive. Does it prove that the function is quasi-concave? Yes, because in fact what we have just seen is that this upper level set is the intersection over P in R plus n of the set of X satisfying this condition. So we have seen that every X in U satisfies all these inequalities, which means it's in this set for every P, so in the intersection. Conversely, if X satisfies all, is in this intersection, then this satisfies all these inequalities, and this is equivalent to saying that f of x is greater than or equal to y. That is, that x is in the upper level set of f corresponding to y. So if you accept this equality, then you must accept that our function is quasi-concave, because these upper level sets are intersections of what? As a function of x, this is a half space. Okay? So actually this is a closed half space. Then the intersection is a closed convex set. So I have proved at the same time that it's quasi-concave and upper semi-continuous, because the level sets are also closed, the upper level sets. Then, about non-decreasing. Well, non-decreasing is obvious just looking at the definition. It could also be proved by looking at the level sets, but no need. I mean, if x increases because p is positive, this inequality will be satisfied for more points, and then there will be more y's that will satisfy it, so the maximum will increase or will remain the same. So non-decreasingness. So we have already proved that this is a nice production function. Well defined, quasi-concave, non-decreasing, and upper semi-continuous. And we only need to see, this is the harder part, but not very hard, that the coast function induced by this production function is the function D. Okay? But I think it may be time to stop, no? So we'll do it this afternoon. Yes, but the cost is the same. Okay?
So it means we produce more, but the cost should.
The smallest cost will be the same. Yes.